Hello everyone, I'm a PhD student from the Institute of Information Engineering, Chinese Academy of Science. Today I'm going to present our work from library portability to para-rehosting, natively executing microcontroller software on commodity hardware. This is a joint work between the Institute of Information Engineering, Chinese Academy of Science, the University of Georgia, the University of Science and Technology of China, and the University of Kansas. It's commonly believed that the Internet of Things, IoT, is emerging as the third wave in the development of the Internet. As shown in the figures, IoT devices are widely deployed in the world. Among them, microcontroller units (MCU) make up the majority with the development of small IoT devices, for example, smart bond, smart door lock, and smart gateway. However, with the rapid development of IoT devices, the security issue is increasingly serious. For example, Amazon FreeRTOS was affected by 13 vulnerabilities in its TCP/IP stack, and Urgent 11 in VxWorks left billions of devices open to cyber attack. Besides, the research work Stone Tools and Frankston found multiple critical bugs in the Bluetooth Low Energy. The vulnerabilities are spread far and wide with the deployment of affected IoT devices. Although the patches are provided by the vendors immediately after the vulnerabilities are discovered, it is still an extremely protracted process to apply them to all the devices owned by different users. As a result, for the vendors, it's critical to do in-house testing before releasing the source code or products, and it's also common that the third party who could access the source code to do some security analysis. But the MCU like a material soft testing environment like the x86 platform. For example, the most popular fuzzing tool, AFL, the fast memory error detector, address sanitizer, the dynamic debug and profiling tool, Guan, and the selective symbolic execution platform, S2E. All these standard software testing tools are not supported, even the most advanced embedded development tools such as MKL and Trace also do not support similar function. Naturally, we consider rehosting the MCU firmware to the x86 platform. To take the advantages of the material testing tools, here we give an example to explain the necessary dependencies of the firmware to run on the x86 platform. This is an MQTT demo project with FreeRTOS. The MQTT library is our fuzzing target. MQTT is a lightweight messaging protocol for small sensors and mobile devices. This project includes 3 core tasks. The MAC task is in charge of receiving raw network packets and transfer them to the IP layer through the queue. The IP task will decode the raw network packets into different protocol packets and send them to the MQTT task through another queue. To run this firmware on the x86 platform, we need to make sure the task and queue of RTOS work correctly. Besides, the whole firmware also depends on other RTOS APIs to deliver semaphore, local mutex, set timer, and so on. This is kernel dependence. Besides, we need TCP/IP, embedded TLS, and so on to resolve the library dependence. Finally, the SPI Wi-Fi library needs to access the Wi-Fi peripheral and receive raw data from the low level. Without real accessible peripherals, the firmware will crash directly while running. This is hardware dependence. Only all these 3 dependencies are met. The firmware could run correctly on the x86 platform. However, the diverse ecosystem consists of these components from different vendors, include RTOS vendors, library providers, SDK vendors. It's a heavy task to understand and resolve all the dependencies among them. Consequently, we propose para-rehosting, a new technique aiming at making rehosting of MCU software to commodity hardware. Based on para-rehosting, vendors or third-party testers could discover the vulnerabilities by out-of-box tools, for example, the address sanitizer. Besides, they could obtain high performance while testing through powerful hardware and running multiple instances. Based on our observation, the RTOS and SDK vendors will generally have CPU and hardware peripheral details to reduce the development burden with 2 portable layers, the processor portable layer and the peripheral portable layer. The processor portable layer generally has the CPU hardware-related codes to support RTOS running. and the peripheral portable layer provides common APIs for the app layer to access different peripherals. These common APIs are also called HAL, Hardware Abstract Layer. For example, HAL provides the same netcard access API for the different netcards installed on the different boards. Based on our research, MCUs follow a similar design, and vendors provide a common HAL to their products. This provides us the possibility to develop a platform to support different ATOS and SDKs from different vendors. With this platform, the developers and testers do not need to read a lot of manual and understand the low-level details of them. Here is the overview of our work. Para-rehosting consists of two components: portable MCU, briefly PMCU, and HL backends. For each ATOS and SDK, the developers and testers only need a very little work to develop a portable MCU glue and peripherals glue to support their targets. The portable MCU component has three parts. First, task simulation. Different from the traditional MCU system, in which a single task monopolizes the processor. In the IoT era, a variety of tasks run simultaneously. This necessitates a multi-programming environment. Multitask support has become a standard feature in major MCUs, which portable MCUs need to simulate correspondingly. We use a process in Linux to simulate the entire MCU firmware and a thread to simulate a task. The thread process model of Linux provides the basis for simulating the task firmware model of MCU. In particular, in Linux, all threads share the same virtual memory space of a process and have their own stacks. In MCU firmware, all tasks share the same physical memory space of MCU and have their own stacks. Next, sysdig. We use the setTimer function to deliver a virtual time alarm signal periodically to simulate the sysdig interrupt, which is necessary for ATOS to schedule a different task. Type I timer virtual is a CTO time of user model, which could avoid the time noise from the Linux kernel. Finally, synchronization primitive. Synchronization is a basis of OS primitive. Once violated, the execution is subject to crash. The portable MCU simulates disabling interrupt by keeping track of the current interrupt status in a global variable. When a virtual time alarm signal occurs, if the global variable is cleared, the handler returns immediately with another global pending indicator set, which indicates the scheduler should be called after exiting the critical section. Otherwise, the handler performs a normal scheduling process. To detect memory error, the most important and concerning part for the tester in a task is stack on a heap. For the stack, fortunately, the Linux thread could support it transparently. However, the memory layout of the task stack is different from the Linux thread. To simulate it better, we also support explicitly manipulate the stack point in each task. For the heap, the ATOS may provide its own implementation instead of using libc heap management. For example, the FreeATOS provide file heap implementation. Here we use heap 1 and heap 3 as an example. Heap 1 uses a global array as a whole heap memory, and heap 3 is a wrapper of libc. ASN could support a fine-grained sanitizer for the libc heap, but different firmware may take different heap management methods. So the developers or testers need to make a decision between a better simulation or better error detection capability. If choosing ATOS' own heap implementation, the testers could simulate the real firmware behaviors better, but may not be able to uncover some bugs. On the other hand, using libc heap implementation will get the full capability of ASN to discover more unknown bugs. However, it's different from the real occasion when the firmware running on the MCU. The second component of para-rehosting is HL backends. To avoid handling low-level hardware details, we leverage HLs supported by major MCU vendors. Specifically, we replace the high-level HL routines with the equivalent handlers on the host. These handlers are implemented per peripheral function. In this paper, we call them HL backends, and they are exposed to HL libraries as a parallel APIs. Here is an example of UART reading function implementation from NSP and STM. The parameter date pdate is a target buffer start address. The parameter length and size is a needed date length. This too is the only necessary part for the function and the program running, so we provide a parallel API HL backend IO read to get input from the stand IO. With this design, the developers and testers could implement a glue layer with a little effort to support different SDK. Subsequently, we categorize common peripherals HL function into 4 types: I/O, storage, computing accelerate, and dummy. And we also implement templates for quick backend development, as shown in the figure. We have developed a para-rehosting prototype on an x86-based PC running the Ubuntu OS. Our prototype supports 9 MC OS, and we focus on testing for popular OS, FreeRTOS, Mbed OS, Zephyr, LightOS, due to their rich library integration. For HAL functions, our prototype covers most peripherals supported in the SDK of NSP and STM. We use an off-the-shelf fuzzing tool, AFL, plus ASAN to test manipulate libraries, and finally discovered 28 previously unknown bugs. 5 of them are confirmed by the CVE team, and the other 19 are confirmed by the vendors. Here are bugs details we found in different RTOS library. Our work reached a high performance based on running directly on the powerful hardware environment, as shown in the table. Another common rehosting method is based on QMU. For example, hallucinator, we have compared our work with it and get a better performance. Most importantly, we could find more unknown bugs than hallucinator by taking advantages of ASAN. To examine the security of MCU firmware, several approaches have been discussed. We categorize them into 4 classes to compare their pros and cons, as shown in the figure. First, on-device analysis. This approach requires real devices to do the testing. It gets the most authentic result, but is less scalable and lacks variability. Second, for emulation. To overcome the performance and scalability issue on real hardware, researchers propose using a full emulator such as QMU to emulate firmware execution. The main challenge is to emulate different peripherals, and there have been some efforts towards this goal. Theoretically, this approach achieves better visibility to the firmware execution. Unfortunately, as far as we know, no existing work is able to precisely support previously unknown devices. Next, peripheral forwarding. As a middle ground solution, a hybrid approach forwarding peripheral access to real devices and run the firmware inside an emulator. However, the performance and scalability issues are still unresolved due to the dependence on real hardware. Finally, semi-rehosting. In semi-rehosting solutions like hallucinator, the main logic of the firmware is still executed inside an emulator. However, high-level HAL functions are identified and replaced with the rehost handlers on the host. As such, complex modeling of diverse peripherals is avoided. Our work needs source code compared with the QMU-based solutions. In summary, our work proposes para-rehosting provide a portable MCU and a HL backend to support porting different RTOS and SDKs for security testing. We have evaluated para-rehosting on multiple platforms, including 4 popular RTOS, FreeRTOS, Mbed OS, Zephyr, LightOS, and 2 SDK from NSP and STM. We have found 28 previous unknown bugs. 5 of them are alien CVE ID, and others are confirmed by the vendors. Finally, we release our prototype on the GitHub. Please start us. Thank you.